Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Last time we began the process of looking at binary stars, and this time we'll finish it off and also talk about what the implications of binary stars are. So we kind of finished off last time by talking about spectroscopic binaries, which are a special kind of binary star that only show up in the spectrum. So what happens is, in say the example that we're seeing here, is that it's actually two stars, but only one star can actually be seen at a time because it's so much brighter than its companion that the companion only shows up as a result of the Doppler shift, the oscillatory Doppler shift of the primary star. The absorption lines that you see here get absorbed, get sent to, we have a laboratory reference, and then the starlight is shifted to the red, then it's shifted to the blue, then it's shifted back to the red. And so the star itself, the brightest star, is the only one that can be seen. And this is called a single line spectroscopic binary. Now, if you can see the lines of both, then they kind of wag back and forth, but sometimes you have such a dim star as maybe a red dwarf star compared to a G-type or an F-type star that you can only see one of them. Such as the example I gave before by R.F. Griffin, where we see only the spectroscopic data of the radial velocity, the radial velocity of the motion of one star. Specifically, the star is HD 105892 from Henry Draper catalog, number 105,982 in the Henry Draper catalog. That is out of the Harvard data set. So this is a binary star, but what we see is that the radial velocity of a particular wavelength of light, and I invite you to go check out that link, and I'll also leave it on the YouTube links, is that the radial velocity associated with that goes back and forth in terms of towards us and away from us in a very, very regular pattern. And this regular pattern encodes a whole bunch of data, meaning notice how it kind of goes up really fast and then down really slow and then up really fast. That means the orbit is inclined with respect to us. It also means that there's an unseen companion. And there's a number of other important things. And the radial velocity itself, as you know, goes back and forth between it because the star system of two is actually apparently rushing away from us. So, or actually rushing towards us, it's minus. So we have the radial velocity towards us, so it actually has a negative radial velocity. So the star is roughly speaking coming towards us, but it's certainly going across our line of sight. But the radial velocity itself encodes a huge amount of information about the nature of the structure. We can determine the mass of the star that's orbiting it, or at least get an estimation, and a number of other things, as well as hopefully the orbital eccentricity and potentially even the type of star it is, by just looking at this curve. Let's look at a really important one. Last time I described that Alpha Centauri AB, which is actually a binary system in of itself, is orbited by another star, Proxima Centauri, and Proxima Centauri's orbit kind of goes all the way around the star. It goes all the way around in the course of a very, very long period of time, maybe 500,000 years or so. Well, I'm not sure the exact amount, but it's on the order of a couple 100,000 years. And so this is an image that was taken by the Digitized Sky Survey from the PAW Sky Survey. And we see there's Proxima Centauri, which is actually the nearest star to us. Proxima Centauri orbits Alpha Centauri. And right now, it's just a little bit closer to us than Alpha Centauri AB, which are two stars, and they're so close together we can't actually make them out due to this particular image, due to how bright they are. But Proxima Centauri is almost lost in the background glow of all the stars that are out there. They're deep, deep, deep when we look in the Milky Way. So all of these stars, only Proxima Centauri has a very high proper motion, as we saw last time what proper motion is. And it also has a very large parallax. It has the largest parallax of all stars, so it's the closest. When one looks at Proxima Centauri and looks specifically at the Doppler shift of that, there's a very strange thing. It's, of course, walking across the sky and slowly moving away from us, and that's what the radial velocity change over the course of 2016 showed. But there's a very, 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 very tiny radial velocity component that is not associated with the proper motion or the radial velocity around the star. But apparently there is a planet orbiting Proxima Centauri. And so this is the pale red dot group. And this was done by a group by Engelada Escudé European Southern Observatory, and there's the link below, and I'll put a whole bunch of links associated with this. Proxima Centauri itself is approaching the Earth about 5 kilometers per hour, about the nature of a walking pace, and occasionally it actually changes with respect to up and down. So we have that we can detect the Doppler shift of the red dots are the actual data, and the blue curve is the best fit to that data. And so what we see is that the red dots indicate that there is, and the bars, those little scraggly bars going up and down, those are the error bars, or how well we know the data point inside the red circle. So it's interesting to note that when in science, you actually have to not just show your data, but you have to show how well you know your data. And so we can see that the bars are fit by the blue curve. And so the best fit blue curve to that data looks like this. And so we see that the Doppler shift seems to have an 11.2 day period, and that is due to a planet orbiting Proxima Centauri. And we'll get to know exactly how we know that in a little bit. And the star itself is a much smaller star than the sun, and the planet is a little bit bigger than the Earth. And so we can actually determine that, and I'll show you how we're going to do that in a bit. That's fascinating. So it's actually would be orbiting inside the orbit of Mercury. So this planet, whatever it is really close to its star. So what do we know about this? Let's go back, and we'll eventually get back to that, but let's look at other kinds of binaries. One of the most important kind of binary stars are eclipsing binaries. Eclipsing binaries, and this is an incredibly important thing to detecting planets around other stars, which is one of the most important areas of research in current astronomy today. Eclipsing binaries are two stars orbiting each other nearly edge on to the line of sight. So we would look at them and they would appear to be wagging back and forth, much the same way if we looked at Jupiter and its moons going around. The orbit of the moons of Jupiter is roughly coplanar to the orbit of Earth around the Sun and Jupiter around the Sun. So we see that Io, Europa, Ganymede, Callisto occasionally pass behind Jupiter, and this is easily seen in a small telescope. And the star and the planets, the moons of Jupiter can be seen to pass in front of Jupiter. The analogous thing is, what if we have a star, and that star has a companion star, and the sum of the light of them is when they're brightest, and then we'll look at this little graph at the bottom. The point one is we see that both stars are visible. Nobody's eclipsing anybody, and so you get all the sum of all the light of the stars. And then if it goes in front of the star, the little star dims the big star. And so you get a big drop of brightness because it's covering up a bit of the star. Inherently, the little star is very dim, so it doesn't contribute much light. So then when it gets on the other side, it goes back up to level 3, which is the standard level of seeing the light from both stars. And then the little star goes behind the big star, meaning it's both little in mass and little in radius. And it's also little in terms of total luminosity. So when it gets its light blocked, it doesn't have as deep an eclipse. You see this pattern in eclipsing binaries where you have one big dip and one little dip, and then a steady amount between them. Or at least that's the pattern that you look for. And of course, nature throws you some really weird things. And the Kepler Space Telescope sees a huge number of these. And that's an amazing thing. But eclipsing binaries, by definition, are really rare because you got to get them all lined up perfectly. And so if you look at the nature of how many stars might be in binaries that actually are eclipsing, we can measure that eclipse. The two stars have to be really close. They have to be perfectly aligned. Stars aren't really that big with respect to the angle that they could actually go by their eclipses. So it's much less than 1% of all the stars, roughly about less than 1% of all stars that are binaries or eclipsing binaries. So they're really tiny. All right, so what the fun part about these is that once you know that a star is an eclipsing data, they are actually the best data of all because the periodic drop is indicative of the period of the orbit. And if you can look at the spectra, you get the speed. And once you get the speed, then you don't even know, and you don't have to know the distance because you both have the orbital speed and the periodicity, and you know the orbital inclination. And so because it's almost edge on, and since it's almost edge on, or almost perfectly edge on, you can actually determine the masses of both stars. And how that is actually done is a little bit outside the scope of an introductory lecture. So so they're actually the best versions of binaries, because you don't have to worry about that orbital inclination parameter. You just go right with it. So partial eclipses are are harder to get if you find partials. But the neatest thing is that you can actually get the atmospheres of stars as the edges. We can see inside the diagram, the red-black diagram, that the edges are kind of sharp. But if they're softer or smoother, or go down and they smoother, rather than being the sharp lines, that they're smooth, that actually would indicate partial eclipsing because of the atmosphere of either one star or the other. And that can tell you information about how extended the atmospheres of the stars are, because some of the light can pass through the atmosphere of a star. And if they're so close that they can actually be tidally distorted, that actually changes the actual shape of the curve, because maybe the stars aren't perfect spheres because they're so close that they turn into teardrops as they tidally distort towards each other. So eclipsing binaries are incredibly important for the study of binary stars, but they themselves have problems if they're too close, and then they're very interesting in of their own selves. So here's a sample of a light curve that we would see from an eclipsing binary. Stage 1, you see both. Stage 2, the little stars in front of the big star, so you get a big, deep eclipse. Stage 3, you're back to seeing both. Stage 4, the little star is behind the big star, so it doesn't dim as much light because the little star doesn't emit as much light. Back to the massive amount in stage 5, and then back to the big eclipse. So this eclipse happens over and over and over again with time. And here's one of the classic examples. This is beta Perseus, or Algol, which I discussed in the last lecture. And we're looking specifically at a wavelength that's 12,000 angstroms, or deep in the infrared. And so we can actually get a much clearer image. And so we're looking at an infrared image of Algol, or beta Perseus, and one of the more important lines, well, the wavelength at a specific wavelength. And so we see, instead of having time, we actually sum up over a huge number of these events, and we combine them together, and we get what's called the phase. And the phase of it is like 0 would be the maximum depth, and 1 would be back to the maximum depth again. And this is similar to actually looking at it from an angular standpoint, or rotating around a circle. Because if it's the same system, you'll always get the same phase, back and forth and back and forth. So you should expect over a large number of observations to build up a curve like this. And that's what people have done with Algol, or beta Perseus, the winking demon of Perseus. And it is the quintessential eclipsing binary. And it takes about 3 days for this to go through a full cycle. And I invite you to go and look it up on the web and see exactly how you can observe the minimums and maximums of it. And it actually doesn't last very long, because if it's about 3 days, then the minimum is only a few hours long. And the lesser minimum, when the smaller star passes behind the big star, is not as easy to detect, but you can actually see it naked eye. That's what's neat about Algol, is that with just binoculars, you can actually, or not even binoculars, if you know when to look and how to compare the stars, this is one of the fundamental things, and that's why the credit is for AAVSO, the American Association of Variable Star Observers, which is where this comes from. So I invite you to actually go and check out Algol on the American Association of Variable Star Observers, or just pick up Sky and Telescope, or any place else where you can find an ephemeris of Algol and its minimums and maximums. The observation of binaries gets us the masses of the stars. And by combining visual binaries and eclipsing binaries, there's only a few hundred stars whose masses are determined incredibly accurately. So all other stars in the sky are actually determined on the basis of these visual binaries and eclipsing binaries, and then looking at the physics of those particular stars, extracting the information from that, and then pushing it out and looking at other stars of similar type. And what we mean by similar type is similar spectral type, like OBAF and GKM type stars, like we saw in the previous lecture. And so every star fall is determined by its spectral characteristics. So all we have to do then is say the mass of a particular star. If the star has the exact same spectrum, it must be that kind of star. So we assume the masses of the stars are related to their spectra. We haven't shown that conclusively yet, but we can actually hopefully determine that that is the case. And by so looking at these events, we can see that the range of stellar masses is about 7% of the mass of the sun to about 60 or 100 times the mass of the sun. But really massive stars are insanely rare. There is a really wonderful study that people do, and that is simply to professional astronomers really are quite interested in how the stellar masses are related to their spectral type. And if we look at their stellar masses, we actually see that there's a distinct relationship between the mass of a star and its spectral type, specifically for stars that we call main sequence stars. We haven't gotten to the main sequence yet, but let's just look closely at this, and we find that we have some sort of interesting relationship between m sub v, which is the luminosity of a star, and its spectral type, OB/GFKM, and the very low mass L type stars, or maybe T and V get to be tossed in there if we want to talk about brown dwarfs too. But we see that there's an extraordinarily tight relationship between a mass of a star and the mass of the star compared to the sun. That's what, like, 1 is a single solar mass, 1/10 is 1/10 of a solar mass, and 10 is 10 times the mass of the sun. And if we look at close binary stars and look at them very extensively and do extensive studies of binary stars, we find that there is a distinct relationship between the mass of a star, its spectral type, and its absolute luminosity. That is critical. And the very fact that there is this relationship is insanely important for main sequence stars for astrophysics. And I'll let you kind of sit on this and think, wow, what is that? And how do we justify that? And I'll get to that. But here we have OBFJKM, which we defined 2 or 3 lectures ago. And m sub v is absolute visual magnitude. Remember, we talked about visual magnitudes very early on. And absolute visual magnitude can range from really quite faint at down to 22 to extraordinarily bright at -6. And our sun is approximately a magnitude 6, absolute magnitude 6 star. And just to remember that a difference in 5 magnitudes is 100 times in terms of brightness. So a 20th magnitude star is 100 times dimmer than a 15th magnitude star, and so on and so on. So this ranges an incredible amount of brightness from, say, -5 down to, say, +20 is 100 to the 5th power, which would be 100, 10 to the, it would be, well, 100,000, 10 to the 10th power, a billion times in brightness between the two. So the brightest of all the stars are almost a billion times brighter than the dimmest of the stars. So stellar masses can be derived from close binaries. They have a distinct relationship to the spectral type, and they have a distinct relationship with respect to their absolute magnitude, which is called which is an incredibly important thing for the future. And that mass luminosity relationship is critical to astrophysics. In this study, we find that for stars roughly below a quarter of the mass of the sun, that's about 41% of all the stars in the sky. And between about a quarter of the mass of the sun and about half the mass of the sun, that's about 28% of the mass of all the stars in the sky. And between all the stars that are half the mass of the sun to about the mass of the sun, it's about 19%. So if we add that all up, we get about 50, 60, 70, 80, and wow, that's a lot, isn't it? 60, 70, 80, 88%, almost 90% of all the stars in the sky are either the mass of the sun or less. So if you look out in the night sky, 90% of all the stars in the sky are smaller than the sun. It used to be thought that the sun was a typical star, and that's why we started with it with all our long thing about the sun. But really, stars half the mass of the sun or less are the most common types. That's fully 2/3 of all the stars in the sky. In fact, I would say it's 70%. 70% of all the stars in the sky are less than half the mass of the sun. So that's a really big chunk. And so most of them are really dim because we saw in the previous that their absolute magnitudes of low mass stars are way down here and they're much dimmer than the sun. So when we think about that, oh wait, what are the ones that are half the solar mass? Those are M-type stars. K and M-type stars make up 70 to 80% of all of the stars in the sky. And way up here in the upper left, the OBAF GKM, those make up the tiniest fraction of the more massive stars. So the brightest of all the stars that you see in the night sky on average, are extraordinarily rare. And that's really interesting. We go to the more massive stars, but between 1 and 2 solar masses, it's about 8% of the stars in the sky. If we then think about 2 to 4 solar masses, that's 3% of all the stars in the sky. And we go up even more and more massive. Such a tiny number of them are more than 20 times the mass of the sun. Less than 6 hundredths of 1%. So 6 out of every 10,000 stars are more massive than 20 times the mass of the sun. So they're rare. And all the bright stars that you see naked eye in the sky are mostly these bright, bright, bright stars, which is really fascinating. So I'll let you go through these review questions. You can pause this, which tells you something about the nature of all the stars in our night sky. But let's go forward. And I promised you something from the very beginning, and this is a view of the southern sky. And this is the view that was taken by the group that was looking for a planet around another star. And that planet is around Proxima Centauri. So we see the great southern sky, the Carina Nebula in the middle. We've got the Southern Cross stacked in the middle. And at the left, the yellow star is Alpha Centauri C, which is very, very close. It's almost impossible to see Alpha Centauri A, and you notice that Alpha Centauri C is actually very, very close. Well, Alpha Centauri is the bright yellow-white star, and that's actually a system of stars. But that yellow-white is the same as the sun. So one of the closest stars to the sun is a G-type star, just like the sun. Centaurus is very, very close to it, and this is the image taken by Beletsky and the group that hunted for it. And this particular image was taken of the observatory that actually made the discovery that we're about to talk about, which is Alpha Centauri A and B, which is a very, very tight star. And we see the location of Proxima in the sky with respect to it. So this is a southern hemisphere only observed thing. And Proxima B was discovered using the HARPS instrument at the European Southern Observatory's 3.6 meter scope down at La Silla Observatory in Chile. We discussed all that, so I invite you to go take a look at ESO's, European Southern Observatory's La Silla Observatory, to see how they actually did discovery and what this telescope looks like. So once again, there's the sky, and we see the Proxima Centauri is lost in there, but just for your own amusement, there it is in the lower right-hand corner. You can barely see it. If you look back and forth between them, you can almost not make out Proxima Centauri, the nearest star to us. And then we look at the star chart to see exactly where it is in the sky, and we can see it's very deep in the southern hemisphere, so it can't be seen from New York City, where I live. And it can't be seen from most of North America. In fact, it's so far south, you got to be below the equator to see it. It's unfortunate. And Proxima is too faint to be seen without using a small telescope. Yeah, that's kind of a bummer, but that's how we go. The key to the discovery is, of course, the spectra. So here are some typical stellar spectra that you might take with a telescope. If you pass it through a spectrograph and take an image of it, you see that there's absorption lines in it, and there's little spectra. So the star's light gets spread out into a spectrum, and there's absorption features. And we're going to look for changes in that absorption features, specifically red shifts and blue shifts. And that's due to the Doppler effect. And the Doppler effect happens as something is approaching us or rushing away from us. If it's approaching us, we get a blue shift because the waves of light get bunched up, and so it goes to a shorter wavelength. And if it's rushing away from us, the waves of light get stretched out, or at least the interval between the successive wavelengths is longer. So the redshift occurs, and we get in the wavelengths are longer. And if there's no motion at all, we don't see any difference at all. So that's how this plot was discovered and found by watching it over the first month of over a couple, like 3 months, the beginning of January 2016. And it was found that there was a planet discovering it. And that planet makes the star wobble because the planet can't be seen, but the spectroscopy of the star evidence that there was a tiny radial velocity shift as the star moved towards us and away from us due to the reflex action of the planet orbiting the star and pulling on the star itself. So even as the Earth orbits the sun, it pulls the sun a little bit off its location because the Earth is a big thing, has a lot of mass, not enough to really swing the star around. The sun swings the Earth around more than the Earth swings the sun around, but the entire solar system, all the planets of the sun tug on the sun, and the sun kind of waggles back and forth as a result, just in the same way that Proxima Centauri gets waggled around by its little planet. And how do we know that mass of that planet? Because we're just saying that the mass is about 1.3 times that of the Earth. How do we get that? And it orbits at 7 million kilometers from Proxima Centauri. How do we get that? That's interesting. Let's see. Because this is the data that shows the discovery of a planet about the same mass as the Earth around the nearest star to the sun. I'll let that sink in for a minute. This is the discovery data that shows it. So how do we get that? And how do we do it? Here's the end result. If we compare the sun to Proxima Centauri, we find that the Mercury's orbit, which is incredibly hot, is very far out. It's at a third of an astronomical unit. But because Proxima Centauri is an M-type star, it is actually much cooler. So in theory, Proxima B is inside of the habitable zone, meaning if you were on Proxima B, there is the possibility that if it had some kind of atmosphere or something, that liquid water could, in theory, exist on the surface because it's not too hot, not too cold, it's just right. It's a little bit of a weird star, and it's a little bit tricky, and it goes around every 11.2 days. And the minimum mass of the planet is about 1.27 Earth masses, and the mass of the star itself is about 12% of the mass of the sun. And its luminosity is really dim. It's 0.2% of the mass of the star, and is a very, very, very cool star at a distance of 4.23 light years. And one of the reasons for this was the study of the stars because it might be something where people want to send a small spaceship to in Starshot. So and all of these information, all this stuff I'm showing you comes from the European Southern Observatory's public website, so you can go grab it at any time and look at it for yourself. In fact, I'm including all the links on this thing so you can go do that. We see that if we compare the stars of sizes of relatively familiar stars, that Proxima is actually really a small star. In fact, it's only a little bit bigger than Jupiter, but it's still a star, and Jupiter's not. Why? Fusion. All right. The angular size, if you were on Proxima Centauri B, if you were on the planet, how big would the star look in the sky? And it's actually much, much, much larger. It would look really big. So if you hold your thumb out at arm's length and try to cut at arm's length during the day and try to cover up the sun, wear some sunglasses, you'll find that the sun and the moon is about half the width of your thumb held at arm's length. Well, if you were on Proxima B would be about it would be half as large as your thumb itself, and you couldn't cover Proxima B with your thumb. It would look really big in the sky. That'd be really strange to see a really big star in the sky, but that's because, well, you're a lot closer to it. So let's make an interesting thought. Imagine that there is this star. It exists. Imagine the planet is there too. And so we see in this artist's impression, because this is not a discovery image, this is an artist's impression, kind of Star Trekker or something like that. We see the yellow star Proxima B and the Proxima in the background. And we see the double star of Proxima A and B in the background to roughly their brightness. There would be incredibly bright stars in the sky because of their distance. But we see that this particular planet that does exist might orbit. It might be a rocky surface. It's only a little bit more massive than the Earth, so it would be physically larger. But what would it be like on the surface? And when we say it's in the habitable zone, we mean that the average surface temperature on this planet is conducive to allow liquid water to be on its surface. That's what we mean by habitable zone. The Earth is just on the inside of the habitable zone of the sun, and Mars is just on the outside of such habitable zone. And we'll talk about that when we get to exoplanets later in these courses. So if you happened to be on the surface of Proxima B, the most likely place where it would be conducive for water to be on the surface is on the boundary between day and night. Because on Proxima B, It is so close to its star that it would probably be tidally locked, meaning it would only show one side to the star. Much in the same way that Io, Europa, Ganymede, and Callisto orbiting Jupiter only show one side to Jupiter, they're all tidally locked. Proxima B is highly likely to be tidally locked to the star. So the star would never change its position in the sky, just the background stars, and you would never see night on the sun side or the Proxima B side of the star. And so the only place that might stay cool enough such that water could exist would be in cracks and valleys right at the boundary between day and night, at the twilight zone of Proxima B. And so you'd have to be right at that edge. It would be and if you went to the other side, it would be perpetual darkness and extraordinarily cold. And if you went to the exact equator where Proxima B would be overhead, it would probably be too hot for life. Or water, more specifically, water, if it exists in liquid form, probably exists right at the boundary zone where thermal stresses could allow some warming and some cooling. But there are other reasons probably why life cannot exist on Proxima Centauri B, because Proxima Centauri is known to be a flare star, so they can emit huge amounts of X-rays, and those X-ray flares, just like the sun has, but they're actually much more violent from Proxima Centauri. And we saw solar flares and the result on Earth, and they're extraordinarily difficult things. So we shouldn't expect that there would be a significant atmosphere on Proxima B, but it's really nice to consider that the possibility is there. And I invite you to go take a look at this from the European Southern Observatory and do follow-ups to see what people have thought in the future. But yeah, if you looked out, you would see actually the traversing of Proxima AB in the distance as you orbited Proxima Centauri. You would see Centaurus AB in the distance orbiting and changing position. So those two bright stars that you see in there would slowly change over the year. Actually, it would change every 11 days. So they would rocket across the sky as it orbits every 11 days. So this is interesting. By looking at the nature of binary stars and eclipsing binaries and spectroscopic binaries, we now not only know the masses of stars, how the masses relate to their brightnesses, how the masses relate to their spectral type, we can also discover planets around other stars. And that's a really interesting thing. And so how we know the mass, we'll talk about next time. See you soon.